All right. Well, thank you,
This
Karen.
meeting is being recorded.
All right. Well, thank you, Karen, for the introduction. And thank you, everybody else, for joining me on Valentine's Day. You decided to spend your day with me. I really appreciate that. So I'll kind of dive right in and talk a little bit about some of the computational challenges we've seen in the area of surgical robotics. So we'll start off with just doing a quick introduction as to different parts of surgery, right? Talking about traditional surgery and then laparoscopic, and then going into some of the robotic areas that are very specific to my talk today. Then we'll take the next section into talking about the computational challenges that we've seen. There's several more that we can obviously speak of, but here we'll focus on imaging, workspace, thermal calculations, and of course at the systems level, which is once you integrate a lot of these components together. After that, I'll spend a good chunk talking about some of the work I have done in my own research and how that has been very similar to the work that's happening in industry with surgical planning and then, of course, optimization algorithms. And a lot of these are eventually used traditionally with the current surgical tools, but then eventually transition over to what's being developed in the robotics field. And then we'll wrap it all up with some industry stories showing you some real working examples of problems that have been solved using some of these tools. All right, so let's go right into the introduction. So when you think about surgery, I bet you're thinking about something that looks like this, right? You have the surgeon sitting at the surgical table with the patient on top, and then you're surrounded by several other personnel, and you're actually making the incision and opening the body up to fix, let's say, remove a tumor or stop some sort of bleeding or injury. And for that, of course, as you can imagine, you're cutting the body open, right? This is open surgery. You would have increased blood loss. That's a challenge. And then if you're having a lot of blood loss, obviously you have to stitch the body back up afterwards. You have really large OR times. And if you're having longer OR times, you're obviously administering a lot of anesthesia to the patients as well. Then afterwards, right, the patient, of course, feels a lot of pain. They have longer recoveries because they have to heal from the actual medical need, but then all the incisions that were made onto their body. They have large scars, and just because you're opening the body up, you lead yourself into possibility of higher risks and obviously infections as well. This is why surgery is moving towards what we call minimally invasive surgery, or MIS. And the way this works is the surgeon actually makes, let me follow with my arrow, tiny incisions based on the need of the surgery. Now, this isn't arbitrary. It's very specific to the need of that surgery. And then once it's decided, the surgeon will pass tools through and do the surgery within the body cavity. Now, the benefit of this is that you're making small, tiny incisions as opposed to opening up the body, which will decrease blood loss, reduce the infection possibilities, and then lead to faster recovery. But of course, it requires a lot more than what was previously seen. You have to first do a process called insufflation, where you pump the body with CO2 gas. And what that does is it inflates the abdomen or the body in almost like a balloon. And that creates more space for tools. So now you can manipulate the tools the way you need to. And as you're adding more gas and things of that nature to the procedure, you also have to have specialized tools. So here, what you see with my arrow is, it's called a trocar. It's basically a tube that ensures that the gas does not escape. So when the surgeon is putting in the tool, removing it, changing it to a different tool, they can do this freely without the gas escaping. And then since you have gas involved, you're also monitoring the system, using a monitoring system to ensure that the body is within the requirements that are needed. Now, there are a few challenges, of course, right? You're not opening up the body. How do you see inside the body? So you have to have visualization tools. And the second is, how do you come up with proper precision when you're working with tools that are harder to manipulate than traditional knives? And this is where the robotics comes in, right? Here, what you're seeing here is one of the most famous systems. It's called the Da Vinci by Intuitive Surgical. It's leading towards more increased precision. And as we develop more and more tools, we're trying to focus towards how can we get smarter visualization of the body inside without opening it up, and how can we have better planning that can give the surgeon better feedback. And the whole idea, as I just mentioned, would be to reduce OR times, decrease the anesthesia usage, therefore decrease the complications, and then hopefully have better patient outcomes. So that's the whole idea of surgery, why robots are such a big part of it. Now let's talk about some of the challenges, right? As you can imagine, robotic surgery hasn't gone mainstream just yet. It has been coming in. People are using it for procedures, but there's a lot of challenges that are still being worked on. So some of those challenges are contributed from the fact that when you build new platforms, you have to make sure that they fit into the current surgical workflow. So surgeons have been working for years, right? They went to school, been in medical school, residencies, fellowships. They've been trained to do a particular task, and you have to make sure that the new tools you build fit within their workflows. And then as you build these tools, you have to make sure that they can have proper data analytics, uh, analysis of the body in some sense that can give the surgeon feedback while they're doing the procedure. Now, that was a high level overview, but what about the hardware that you're designing, right? So on your right, you're seeing some of the surgical tools that are part of the robot. How do you build a tool that can have really large workspace coverage that is needed for the procedure? I'll talk more about what workspace really is. You have to ensure that there's no collision when the robots are moving. And the whole idea is to also minimize the footprint, right? What that means is that when this robot is in the OR, you're also having several other personnel working besides it. You have to ensure that there's no collision, there's enough room for the surgeon or any of the other personnel to touch the patient and get involved if need be. Now, development of such complex systems, as you would imagine, would require a model-based design, basically coming up with the design of the system, and then analyzing it, ensuring that you're happy with the performance before you go ahead and build something so complex. Now, when you build such complex systems, and I'll talk more about each one of these as we go further in the presentation, how do you integrate it at a systems level, meaning how do you put everything together and get it to do what you need for it to do, and then test for that, and then ensure that your algorithms are working the way you want, and eventually deploy it to hardware. And let's say you're able to deploy it and get it working, but now you have to ensure that you can monitor the system's performance and maintain the system as it becomes commercialized over time. So I'll step into one of the most important aspects that are quite challenging in this field, right? And you probably guessed it, that it is visualization. How do you see inside the body cavity while doing the surgery? So I did see on the ICME website that groups are working on analyzing MRI data. So it fits really well with the talk portion right here. So when a patient comes in, they get imaged, right? If they have an issue of some kind, they'll go through either a CT scan or MRI. And these images will eventually get put into a format called DICOM. And that doesn't just contain the medical image, it also contains a lot of information regarding the image size, pixels, maybe some sort of confidential information. Now, how do you pull this information into some software and analyze it? That's quite complex to do for different hospitals in different settings. So I'll show you an example right here. A patient comes in, they get a CT scan, which is just layered scans, right? Planar scans of the body. You want to create a 3D mesh of some kind once you import this into some sort of software. So here we import it into MATLAB, and now we can actually create 3D models of the different organs. But these models of this, what you're seeing here is the lungs. This is only as good as you segment, right? Segment is cutting out the tissue and then cutting it out in layers and eventually building those layers into a 3D piece. Now, how do you do that precisely, right? And how do you do that for each patient, really? Because everybody is similar yet very, very different. So here I'm showing an example of how we come across that using some of our computational tools that we've developed. What you're seeing here is the lung being cut out and then part of the other tissue that are not important being masked. And that way we ensure that we only pull out the right parts of the tissue. And a lot of this can be done using computation on density, pixels, and different type of imaging techniques. But as you imagine, it is quite tedious, right? It takes time to go one slice at a time. So there are new algorithms that are being developed that can use smart techniques to do this automatically, right? And here what you're seeing is one of our deep learning toolboxes that we've been working on, where you can actually segment out the tissues, train your model, and then eventually get the system to pull out that part of the tissue automatically. And it is not a trivial thing to do, but it is very, very much needed in the surgical robotics field. So what you're seeing here is brain tissue, and we've segmented out a certain portion, and then you can use that to actually create a 3D model. So here you're seeing the brain, that you can actually manipulate the 3D tissues to look at it in depth and from different angles, and associate that with your surgical plan and make sure that it is how you envision it in the 2D scans as well. Now that was from the imaging side. Of course, it's a very complex issue, but I definitely wanted to put some light towards it. Now the other issue becomes that as you start building these robotic tools, how do you get the robot to work properly in your environment? So for those who are familiar with robotics, this will be a very, simplistic concept. It's called inverse kinematics. You have some desired trajectory that you need to follow for your robot, and you use inverse kinematics to calculate all your joint angles. So each joint of the robot has a motor, and you calculate the angle that's required to get the robot to do what you want. Very traditional robotics 101. What do you do when you have multiple robots, right? So here you're only seeing 2, but in a surgical setting, you have anywhere between 4 to 6 robots. And it could even be more as there's new advancements in the robotics field. Now, it's not about following the trajectory alone. You also have to think about the collisions that can occur. So what you see over here, if you follow this particular path, you see that it just right over here, they collide. And these are type of things that you have to use your computations to account for in your surgical planning. And now imagine having, as I mentioned, 4 or 6 arms. This becomes a very complex task. Let's make the matters a little bit worse. You see the overlay of the human body. Now you have even more constraints that are added to this problem. How do you model that while accounting for the robot kinematics, the addition of other robots around your environment, and now the human body that you're working on that has a lot of limitations because of the important critical structures within it? And let me make it a little bit more complex just to shed light towards why so much computation is required to solving these problems. So if you use your imagination, this is a person laying on their side. So what you're seeing is 2 kidneys. Now, if a surgeon was supposed to work on this, they would decide where they want to make the incisions, and they would pass what we call a laparoscope or some sort of surgical tool into the body, right? But now you are bounded by this portion, this red dot, basically, which is the remote center of motion, or RCM for short. So at this point, the only thing you can really do is torque the tool in this way. And that RCM becomes your pivot point. So if you were to look at your workspace, right, the area that this device can cover at this point is probably going to be in something of this red region. It will look like some sort of cone, really. And you really can't work outside of that. And that's another constraint you have to mathematically account for. And let's add another robotic tool into the mix, right? This is a very simplistic parallel mechanism that's used in surgical robots. It's obviously housed in a beautiful device inside, but inside this is the type of mechanism you would see. And this is how you use geometry to actually constrain your robot or your tool at the RCM, right? And that requires obviously very complicated mathematics. And as you develop new and new mechanisms, you have to think about how to put that into your controls. Or you can decide to keep the design very simple and then use more software-based constraints for your control. And those also require several computational needs. So that was from the workspace portion, right? Now, again, I'm highlighting some of the key points here that are large problems in surgical robots. So you have your robot arm. And as I mentioned, you have anywhere between 4 to 6 arms, right? This arm will have motors at each joint. So any robot arm specifically can have anywhere between, let's say, 6 to 12 motors or even more. So you're imagining a lot of motors in each of the arms, and there's 4 to 6 arms. Now let's look at just one part that's actually a very critical part. This part could house several other motors, and those motors will be used to control the instruments or the surgical tools that are attached to your arm, right? So imagine you have a pair of scissors, surgical scissors, of course, that are attached here. How do you manipulate the scissors? You do that with the motors. And if you have motors here, you obviously have to have some sort of chips or microcontrollers to control it, which are a heat source. And as that heat increases, you actually have to ensure that you don't reach a threshold that burns out your motors or your chips. And FDA also has regulations that need to be met if you want to get FDA clearance and get this onto a patient setting. So one way to think about doing something like this is to take your CAD model, convert it to an STL file. This is something that we've done. There's, of course, other ways to go about the problem. Convert it into a mesh, and then set boundary conditions based on the material that is used for this type of housing. And then do a thermal analysis to see what type of heat gradients you would have in a part of this design. You can use parallel computing to get several data points throughout your tests. And then you can use fitting to actually graph and understand what are your actual temperature thresholds. And for this example, we see that in this type of scenario, you may have 311 degrees Kelvin, and now you can determine if that design needs to be reworked before you actually build it, or it is good to go. But what if we want to automate something like this, right? So let's imagine you have a permanent magnetic synchronous motor. It's a particular type of motor. And as I mentioned, one of the challenges can be that if it heats up, you would have destruction of the motor itself. And some of these parts are very, very expensive. So you have to think about it before you actually go ahead and build it. And if I was to measure the heating across the system, I would have to incorporate each motor with several sensors, right? And I already talked about how many motors and robot arms we have in a surgical setting. And you would also have to understand very deeply how a system like this works to know where to house the sensors. So there's other techniques that you can use with deep learning, with using just neural nets. So you can create relationships with torque and speed, which are two obvious measures of motors that can be easily calculated. And then you can collect previous data from the performance of similar systems that have been used in the past to train a model. So in this type of example, we use ambient temperature, the liquid coolant temperature, several other current voltage, speed of the motor in your training models. And then you can use a deep network designer to build a model that can fit the needs of your problem. And then if you graph and actually test your system, you can see that a system, an algorithm of such kind can actually give you pretty good control of your predictions. And you're seeing here on the right side that the errors are very minimal. They're basically baseline around 0. And you can see that the tracking of your predictions and actual test is quite well done. And this can minimize the use of sensors in your system. And this will be a small part of a big problem that will eventually lead to having deployment of these complicated systems. Now, another part that I would like to dive into is how do you tune these motors, right? So if you're familiar with robots, a robot that can work in 3D space is called a 6DoF, or 6 degrees of freedom robot. And a 6DoF robot will have 3 translations, so it can move in space, and 3 rotations. So to have 6 degrees of movement, you also need 6 motors. So here's a simulating model of how that would actually work, right? You would have the motors. So imagine your plant is right here. This is your system. And then you need to tune each motor to work with precise accuracy, as especially in a surgical setting where even sub-millimeter accuracies are important. So you would tune the motors. And this is how you would model it, right? So if you look at it in complexity, you have six motors that all require either some sort of PID, or in this case, PI, which is your proportional gain, your integral gain, and then if you had a derivative gain, you would have that as well. And each one of these helps improve the performance of your system to its desired motion. Now, in individual settings, you would actually just tune one gain at a time. You would either guess, or there's mathematical equations you can just kind of fit the performance of your system into. But what you're doing at that point is you're basically tuning one motor at a time and not accounting for all the other motors that are adding to the errors of your performance, because you're only tuning one motor at a time. But if you use a function which was developed using computational math called system, it can help you tune a lot of these parameters together, right? You can formulate a frequency domain optimization problem, and as you develop these problems, you can compute what are the gains that are required for each of your motors while incorporating the issues that are happening during movement. And this is exactly just showing you an example of how computational mathematics plays a big part in solving these problems. Now, I'll give you a high-level overview of what's going on, right? So especially in industry, when you have such a complex system as a surgical robot, you can imagine that there are several teams working on such a complex system. You have a controls team that is ensuring that all your input and outputs are performing the way that you would want it to. There's safety features in the system, and they are also performing well. Then you have a hardware team that are building your CAD models, right? You're designing your system and deciding how the system will maneuver. Then you have your electrical teams that are ensuring that you're having good communication between your motor drivers, and then eventually leading to control of your motors. And as you can imagine, each of these tasks is super complex. And as you build it among your teams, and then you do go through a whole V&V type process. You verify that the system is working the way you designed it to work. And once it meets your requirements over several iterations, you send it off to the systems team that will integrate all this together and test it to ensure that the system is working. And this is similar to the aspects of model-based design, where you want to ensure that the system, these very highly complex systems, are working the way you would want them to before you go ahead and build something so complex. And that is something that we see that we can do in some of our tools that are being developed. Now, again, I'm giving another high-level overview. As you have development of these tools, right? You planned it, you designed it, you built it, and then you retested it. And then you'll have the operations where you actually will one day deploy it, and this will operate. But you also want to be able to monitor it to make sure that the system is working up to par. And if not, you can predict some of these issues that can arise. If not, then you would have to stop the use of that system and go back and make those corrections. So as part of your life cycle, you can add this feedback component where you can measure what's happening in the system, add that to your plan, and then build, redesign, or if needed, and then rebuild and release over iterations. And one part of that is you can use digital twins. And for those who are not familiar with digital twins, that is just basically a digital representation of the actual physical assets in your robot, right? So let's say you have a motor and you want to see its performance. You can build a digital twin, on a computerized version, to work simultaneously that can detect faults, predict your maintenance, and help you make decisions before you actually have an issue. Let me give you an example, right? So you have your physical system running, and then you can use a digital twin to evaluate the behavior, let's say, of a motor. And as the motor performs, it collects data simultaneously, and you can get an overall understanding of the system's behavior. And when it hits, let's say, a region that is a no-go for you, right, where that is not an operational zone, you can stop the system beforehand and think about how you can change your design before you actually have major issues, and you can predict this beforehand. So what I did right now is I shared a lot of problems that arise in surgical robotics and why so much computational needs are present in developing new tools that will eventually solve some of these problems. But I want to also step through an actual problem with a problem formulation, and then talk about how I went about working on a certain problem myself. So I hope you're all with me. We'll keep going forward. So the problem we're solving today is called percutaneous nephrolithotomy. It's a procedure called percutaneous nephrolithotomy. We'll call it PCNL for short. So this is just a surgical procedure where patients come in with kidney stones, and these are not your small kidney stones that will pass. These are very severe cases, right? And as you see in this nice little diagram right here, they can be lodged into what we call the renal pelvis. And then they could be in the ureter. This is where urine travels through. And then you have these red pockets called calyces, and that's where urine will eventually collect and then should drain, but it's being blocked by these kidney stones. This is actually a pretty complex problem to solve in real surgery, right? Especially because you have to decide where do you want to make the incisions to get access into these cavities, these calyces. So that is part of PCNL planning. So just to give you like a visual representation, you can follow each of these arrows. You can have incisions made in any part of the skin accessing into the kidney. And theoretically, there's infinite solutions to this problem. So where do you make the incisions? And if you were able to compute this mathematically, you can actually optimize your planning using some of these pre-operative images. And then you can eventually use your planning for the surgeon or for your robot that will eventually be built to solve this problem. And this is how it looks in a CT scan, right? So the surgeon doesn't see this beautiful colored image on the right. They see it in black and white. The whites are their stones, and then they have to determine where they want to make the incisions. Now, to give you another graphical representation of the problem, during the actual surgery of this type, the surgeon will lay the patient down. They will take what we call a fluoroscopic image of the patient. And that way they can see where the stones are in real time during the surgery. Now they have to determine a few things. One is your percutaneous axis. All that is where on the skin you want to make the incision. And as I mentioned, you have theoretically infinite solutions. You can make an incision anywhere along the skin, right, the outside. The second is where do you want to make the incision on the actual kidney? That will give you access into the calyx or these tunnels. Third is your surgical trajectory, the path that you can follow to take out all the stones. And if you do this correctly, or if you find the best and most optimal solution, you would have a large number of stones that get removed. You will also reduce intraoperative bleeding, and you'll reduce what we call number of sticks. So sticks are the number of times you actually make this incision to get inside the body. The goal is to do it all in one go. But if you can't, you may have to do it twice or maybe even 3 times. And that is not ideal. But this planning varies surgeon to surgeon. Surgeons are trained in this procedure for many years, yet they all do this task quite differently. So what is the right path, right? What is it that will lead us to the best solution? And if we can figure that out, well, we can actually have a surgical planning algorithm that can be utilized by all surgeons for training and for actual surgical need. So this is what we did here. We decided to first get 8 experts, right? 4 urologists, which are the actual surgeons doing the procedure, and then 4 radiologists who are trained in actually deciding where the incision will be made for PCNL, the procedure. And as I mentioned, that everybody looks at the same parameters, yet everyone decides where to make the incisions quite differently. And that's something I learned with spending a lot of time in the OR with them. Now, what are the engineering considerations I should take into account when solving this problem, right? I can use deep learning, of course, that is the best way normally comes to mind, yet I don't have prior data to train my models here. This is a very unique problem, and there isn't a whole lot of information present for training systems. And as I mentioned, there's no consistent methodology, right? Each surgeon is doing it quite differently. All right, then let's make a mathematical model. Yet mathematical models require a lot of assumptions, and sometimes they don't translate equally into the real world. Or you can use pre-made robotic path planning algorithms. So for those who've taken robotic classes, this is very, these are some common terms: A-star, Dijkstra's, RRTs. Those are common robot path planning algorithms. But they require a start and end point to find your solution. And as we mentioned, we don't know the start and end point. We just know the task that we need to complete. So then the third option that comes to mind is using what we call genetic algorithms. It is a mathematical optimization that can account for non-obvious parameters. And using a cost function, you can actually try to minimize and find the best or most optimal solution. The best aspect here is that there's no prior data required, and the implementation analysis due to tools that are already developed is not that challenging. So that is the route that we decided to go here, right? And for those who are not familiar with genetic algorithms, I'll talk to what that is. Here's the cost function that we defined, and the next step, I'll talk about the parameters. But after spending a lot of time in the OR, I was able to decide what aspects are important to the surgeon, right? They want to minimize the length traveled to get to the kidney. You have to obviously have obstacle avoidance for the lungs and the other tissue that you don't want to pierce. You have to think about your tool geometry, your tissue densities, and other different parameters I'll talk about in a second. But what about genetic algorithms? How does that work, right? It is basically an idea of natural selection, the way biology works, and made into a mathematical format for literally any optimization problem. So initially, you just find randomized solutions. You make this cost function, and you let the computer find set number of random solutions automatically. Of course, some are going to be good, and some will be horrible in this sense. Then you do a fitness assessment by measuring the cost associated. And then you divide your good solutions from your bad, right? The solution with a low cost are meaning to be more optimal, minimized, and we'll take that as our top half of our pool. And just like random selection, we pick from the fittest pool. We find 2 strong mates, we break them in half from their solution and take different aspects of the solution and cross it over and induce a randomized mutation, which is basically a non-known deviance into the solution. And then we compare what we call as our offsprings from the parents. We see if the cost of the offspring is actually less, meaning they're more fit than their parents. And if they are, the parents die out and then the offsprings take control of the pool. And as you do it over and over again, you get a fitter population. And if you were to graph that, this is how it would look. You would see that the cost of the overall population is very high, And over the iterations, it hits a threshold and minimizes to some threshold. And once it hits that threshold, the system stops because you have optimized. Now, if we're to graph it, you can see over here that initially you have randomized solutions followed by these circular circles, right? Really. And as you optimize, you converge to a global minima until you hit a threshold, and now you can stop your solution. Now, to kind of talk about how this is fitting into our workflows, you have a patient that comes in, they have some sort of concern, something that's hurting, their back hurts. So the surgeon will order a CT scan. That scan will get segmented either manually or using some of the deep learning methods. Then the solution will create that random solutions that I just talked about. We'll determine where are the skin surfaces, where are the calculi, which are just another fancy word for stones, and then other aspects that are medically relevant to the kidney, the renal pyramids and renal axis. Those are just some medical terminologies. And then you optimize over the cost variables. And then the output is three different things. You get a percutaneous site where you make the incision on the skin, where you make the second incision in the kidney, the renal aspects, and the trajectory through it to get through the stones. Now let's just spend a quick second on the constraints and why they're important. So of course you want a shortest path, right? If you have a very long path, they may not fit your surgical tool's length and capabilities. Of course, you have to avoid surrounding tissues. I talked about that. You don't want to pierce lungs and any other critical structures. And then you have to think about the curvature and limitation of your tools as well. You may have a traditional tool that's very rigid and straight, or you may have robotic tools that are being developed that are flexible and that can navigate more curved paths. And that has to be a part of your cost function. Tissue density, do you want to go through hard tissue or soft tissue? Soft tissue just sounds, it's less painful. And then as you have a solution, you want to map that back onto your workspace of the human body and see that is the trajectory actually doing what you want it to, and covering in blue what you see as a kidney stone, the kidney stone. And to ensure that this type of formulation actually has clinical relevance, we do an assessment prior to actually doing our studies. You take into account all constraints and you let it optimize so that that genetic algorithm I talked about, that runs anywhere between, let's say, 200,000 or more iterations. And then eventually it stops when the stopping criteria is met. And this is the type of solution we see. At least visually, it looks like a good solution. So what you're seeing here in purple is the lungs, then your liver in green, your kidney, and then the kidney stones in blue. And then yellow is your skeletal structure. Now, what if I was to manipulate the tool curvature constraint and add a more flexible tool, and we see that the solution becomes more curved? That's a good sign. That means the curvature parameter is doing what we want it to do. And how about if we remove the density constraint to make the problem simpler? Then you see that it pierces skeletal tissue, bone, right? Basically, that won't really work for some of the needles. They may just break. And then if you don't take obstacles into account, you'll find a more straightforward solution, yet you'll pierce the lungs, which isn't viable. So at this point, we feel pretty good that all of our cost function parameters and our constraints are looking pretty sound. Now let's talk about the whole research workflow, right? As I mentioned, you have the segmentation of the tissues, right? Then you feed it into this optimization that you just modeled and developed. Then the genetic algorithm does its own thing, right? Does a selection, crossover, mutation until it hits its threshold. And then for the fourth part, we actually have the experts, right? The 4 urologists and the 4 radiologists provide their own solution, the way they normally would solve this problem. And what they do here is they look at a CT image, which you're seeing on top, and they decide where they will make the incision. So here they decided this is where they'll pierce the kidney. And then they decide somewhere over here, they'll pierce the skin. And then they find the trajectory along it. And then we actually 3D modeled it for them, so then they can see that their decision is the way they would want it to be. Now, each expert did that, and then we mapped the solution by the expert to that of the algorithm. So the green is that of the expert, and red is of the algorithm. So pretty interesting take here, right? You're seeing 15 cases. I know it's a whole lot to look at, so I'll kind of guide you along here. Let's look at this right here with the mouse, is the pointer. Really nice to see that our algorithm is performing very similar to the surgeon who has years and years of experience doing something like this, right? But then in other cases, let's look at over here, the third one on the top row, you see that the surgeon or the expert decided to go from the top, while the algorithm decided to go from the bottom. Now it becomes a little subjective, right? Which solution is actually better, and which one would we want to feed to an automatic robotic control eventually? So what I had the surgeons do is, or the experts rather, rate our solution in comparison to their solution. So a rating of 1 would be that the algorithm performed in an unacceptable manner. We will never use this type of solution. 2, it's an acceptable solution. You can use either the expert solution or the algorithm solution. Or number 3, that the algorithm performed maybe a little bit better than the expert had decided to go about it. And then we see that after having 15 cases with 8 experts, we get an average rating of 2.6, which is a pretty good rating. 92% of the cases, the algorithm performs in an acceptable manner or better than initially planned. That was very promising. So we look at more aspects to ensure that the solution that we computed is performing up to par. And we see that the average angle at which the experts come into the body was 151 degrees, with the algorithm 152 degrees. Again, that's very promising. And then the third, we have to ensure that our solution, our length, the track length, is adequate for a traditional tool or robotic tool to follow without running out of room to move forward. And we see both are about 80 millimeters. Again, a very promising solution that we were able to compute. We'll want to take it one step further and actually see, is our system actually mapping well? So we do here, what you're seeing in the green and the red, is the kidney stones. And then the color represents how much kidney stone would be covered by the algorithm's solution. And this is a static case, right? So I have to admit, it is not a complete real world scenario, because in real settings, stones will fall due to gravity, and then you can catch more stone. But at least in a static case, you can see that we were able to capture quite a bit with our algorithm. The cone is the expert's solution. So how much coverage do we get from the expert's planned solution? And when we compute it, we see that the optimization can cover 57.1% of the stone on average, while the expert solution did about 32%. And this is, of course, again, as I mentioned, a static case, which was very, very promising for us. And this is just an example of how you can go about formulating real problems to develop real tools and real algorithms that can solve real problems. And after you have these solutions solved, they can be deployed to the next stage, which is automation using robotics and tools of the kind. So in my final section, I will talk about some of the industry stories, things that have actually happened in the industry using some of these type of tools. So I want to first leave you with a bottom line here, right? Computational mathematics can really be used in various engineering fields, right? So you can use it to solve or problem formulate really complex issues, ranging from robotics and surgery to batteries and electrical vehicles. And we at MathWorks are also a part of industry, and we use a lot of mathematical computations to develop some of the tools that we develop that help solve real world problems. And that is a big part of our contribution in industry, which helps speed up others' engineering and science developments. So some of the tools that we have computed mathematically and then deployed have resulted in solving issues for aerospace and defense, to biotech and pharmaceuticals, all the way to neuroscience and even software and internet related challenges. And I'll talk about some specific surgical robotics related cases here as well. So Preceyes, they are a company out of the Netherlands. They actually develop surgical robots, full platforms that can do surgery on the eye, which requires a lot of precision. So in this case, Preceyes actually used the tools that we have developed using a lot of our, as I mentioned, computational mathematics over time, and they were able to use that to formulate their problem, develop a controller that can actually control the robot, build a system to test it to make sure that it is working the way they would want it to, and then actually use what we call a coder to deploy to hardware and get the hardware to actually be controlled by the test code. And this was actually used for patient safety assurance, and then eventually being deployed to real systems, real problems. This is another example. This is Corindus. It's a very known company in the field. They actually designed the entire platform on MATLAB and Simulink using some of the computational tools that we've developed. And they were able to showcase how a coronary intervention can be done remotely from a faraway location, telerobotically. So you have a surgeon or an expert sitting at a faraway station, and they can control a robot that's maybe in a remote area or a test setting. And they were able to do the world's first inhuman telerobotic procedure of this kind. And they were able to develop the system very, very quickly due to the tools that we have developed. And that really helped decrease the engineering load and help advance science to speed up its development. And with that, I did present a whole lot. Hopefully you were able to absorb it. And if not, I'd be happy to take questions following this just now. So thank you for listening.